In my last video, I demonstrated and described the operation of this debugger board that I built for my Ben Eater 6502 computer. This board lets you step through each instruction individually, step by step, and displays the registers on the LCD. It displays the A, X, Y registers, all the status flags, the program counter, the stack pointer value, and the stack pointer and the value that the stack pointer is pointing at on the stack. And it lets you push this button to move instruction by instruction and see what those values are. One of the problems with the board, though, is what if you're actually using the LCD in your code and you're displaying something on the LCD and you want to see that, but you also want to be able to run the debugger board. Well, I've written some additional code that makes it so that you can do that. So I'm going to show you this code. If I press reset, I've set a breakpoint. So after displaying a W, then it stops. It stops and it's waiting for an instruction. And if I push this button, it'll just go through and write out the whole thing. My Hello World program here, which has Witness Me, Shiny, and Chrome. But if I were to reset this, so it goes back to displaying just the W, and now I turn on debugger mode, I can go step by step through the code just like before, but it will show me each step of the way what's on the screen. So let me show that. So I'm going to press the button, and here it's going to show me that I'm loading A with a 6.9. Program counters at 8011, and of course the stack pointer, which I'm not using the stack at this point, and so forth. And now, if I press the button again, it goes back to show me what's on the LCD. I press it again, it's still showing a 6.9, but now here we can see that we're going to jump to COA4, and if I press the button again, it now shows that I've printed an I on the screen. And as I go, it'll keep showing me what's on the screen, switching back and forth between what's on the screen and displaying the value of the registers and the status pointer and the value on the stack. And so I can just keep stepping through, and it'll just keep going through there. And I also want to display here, I'm going to show you something here. So here I am going character by character, but I also wrote a print string command that I want to, or a subroutine that I want to show you. And so when I press it next time, it's going to go one more, 2-1, that's exclamation point, one more exclamation point. And now it's still has the exclamation point, but now it's going to tell me that it's going to run to, hold on. Now it tells me it's going to jump to C0D1. This is the location of my print string subroutine. And next time it runs print the whole thing, Shiny and Chrome. So let me show you the code for how that works. So here you can see that I load A with a W and I run print car and that displays the W. And then here I have my breakpoint. This is the wait command. I am not compiling with the WDC02 extra instruction, so I put it in as a byte. And as I explained in my last video, this is the wait command, but I remember CB by calling it a controlled break. So that is the wait command, and now when the computer gets here, it'll wait for an interrupt. And of course, pushing that red button is what, the red button here is what provides the interrupt that it's waiting for. Then I'm just here individually doing a load A, print car, load T, and so forth. So I'm just loading each letter into the A register and then jumping the subroutine print car to print it. I do that all the way through for the Witness Me and the 3 exclamation points. But then here I'm loading X with the low order of the location of this message flag. So the message flag is here, and this flags the memory location where this bunch of blank spaces plus Shiny and Chrome are in a string. And this is the ASCII Z directive, which will put a a null character at the end of Shiny and Chrome. And so I'm loading the low order of that into the X register and the high order of that into the Y register. And then I am jumping subroutine to print string, which you can see here. So what do I do here? First I push A because I'm going to be using the A register, so I want to preserve its value. So I push A onto the stack. And then I transfer X to a variable called message, which I've defined up here. And you can see that I've just defined that as the byte 00 and the 0 page variables. And the reason I'm putting in the 0 page is very important because I'm going to be using the indirect indexed mode, which can only be done from a memory location that's on the 0 page. So I store the low order byte, and then I store the high order byte from Y. And then I load Y with a 0, and that's the Y register is holding the offset from the start of the string. And then I set a flag at this memory location, print, dot print. The dot in a directive tells the assembler that this is a local variable. So if you refer to dot print from outside the print string subroutine, well, anyway, outside of between the print str and hex to char, anywhere outside of that range, it wouldn't recognize it because it's local to between those two non-local variables or flags. So anyway, I load A using the indirect indexed addressing mode. I load A with the value that the memory location at message and message plus 1, comma Y, the value of Y. So of course that will be message to message plus 1, which if you remember is going to be the memory location at MSG that I had earlier. And if equal, branch if equal to done. So if equal, that means I loaded that null character, or the null 0 byte at the end of the string, and so I'm done, so I'll jump down to done. But if I'm not done, then I print the character, and I increment Y, and I jump back to print, and I'm prepping for the next character. So this will just keep going until it gets to the 0 byte that the ASCII Z directive put at the end of that string. And of course, in case it's not obvious, like the reason I have all these spaces here is I've printed witness me, but my character, my LCD is only 16 characters wide, but there's actually 80 characters in the LCD controller's memory. The first 40 are the first line, and the second 40 are the second line. You can't see what's off to the right of the LCD, but those memory locations are still there. So I'm just filling them with spaces. I could fill them with anything. Enough spaces so that when I come back around, when I do the next one, it's going to be on the second line. And that's how you get Shiny and Chrome to be on the second line. Okay, jumping back down here. So basically that's all I've done is I've printed that string there. Then I pull A back off because I screwed around with it. So I had to push it onto the stack. I'm pulling it off the stack and return to subroutine. And that brings us back to print string. And after that, I'm just going into this loop so that when I press this, you can just see I'm just jumping back to 8052, 8052. It's just jumping back and forth. It's just staying there at 8052 because it's just jumping back to itself here. Now, let's take a look at the changes that I made to the non-maskable interrupt. So this is all the same. I'm saving all of the registers and the program counter and the status register and the stack and the value at the stack. And I'm restoring the stack. And then here's where I stop and wait. And this is where it's just displaying whatever's on the screen because I just stopped here. I haven't made any changes to what's on the LCD, so it's just waiting. But when so here it's just waiting for me to push the button, and then after I push the button, that creates the interrupt that tells the computer to continue on, and so the computer continues on to I didn't put it in debug mode, so it continued on and went to the end of the program. Let me restart it, put it in debug mode. So now I'm displaying all the, as I just explained in my last video, I'm going to display what's on the LCD, but before I do that, I have to save the current state of the LCD, and that's what I'm doing here. So here it says save the current state of the LCD. So I have a variable called LCD data that I'm loading into A, the low order of, and that's the low order address of the LCD, and I'm storing that to something I called LCD vec, which is a vector in the 0 page. And again, I'm going to be using the indirect indexed addressing. So I have to have that. I have to have I have to say where the data, the LCD data is stored. I have to put that memory location into the 0 page. And here I'm putting it at FE, and then of course the high order will be at FF. So I'm storing that. I'm storing A into LCD vec, and then I'm loading the high order bit of LCD data. And LCD data, by the way, is the actual location where the data is stored. And here you can see in the variables that I set up for the debugger, I created a new one called LCD data. And so this is going to be at 1FF8, value of SV, minus 81. So it's going to reserve 81. That's decimal 81 bytes for the LCD data. That's the reason I need 81. I need 80 for the actual value that's in the data. And the reason I want to store the stuff that's off screen is that in other modes of this LCD, you could be scrolling. And so those would scroll onto the screen. So you want to make sure you store all 80 of the bytes of data that are stored in the LCD controller's memory. And I also need one more to store the address pointer. So that's why I have 81 reserved there. So this is storing low order into LCD vec, the high order into LCD vec plus 1, and now we're going to be able to index off of that address that's stored in there. Then I'm jump subroutine LCD address. So this gets the address counter into A, and that's a new subroutine that I wrote. So what I do in LCD address is I'm going to output in the A register the address counter value. That's the address counter or address pointer, it's called in the LCD controller. So I'm setting all the pins on port A to input because I'm going to be reading. And then I'm storing that to DDRB, the direction register for B. And then I'm loading read-write. So I'm setting the read-write to read because when this is high, it's a read, and clearing the register select in E bits. And then I'm storing that to port A, and then I'm loading. Then I'm loading A with a read-write bit and the enable bit. So this will set the enable bit, and I store that to port A. And when I do that, that's when the information is going to be. Oops. That's when I store this to port A. Then the enable bit is high in the control in the LCD controller's control register, and so that is good. It tells the LCD to put the data of interest onto the data bus at port B. So then I load A with port B, so that reads the data from port B. And this is very much, if you look at this is exactly like the wait routine. So if you went through the wait routine with me, this is so far doing exactly the same thing as I did with the wait routine. But the difference is with the wait routine, I was interested in what was in the the highest order bit, which is the ready bit. But here I'm interested in the lower 7 bits because that's the address. So I get the LCD address counter that loads that into A by calling the LCD address. Let's see. So where were we? Yeah. So we loaded A into port B, and then I push A onto the stack, and then I AND it with the ready bit, and that masks the ready bit, and I keep doing that while it's busy. So this is doing the exact same thing that the LCD wait does. I can't just call LCD wait here because. For two reasons. Well, the reason is because I need to push this A onto the stack, and LCD wait doesn't do that. And if LCD wait did do that, then that would screw it up when you're just using LCD wait. So instead of calling LCD wait, I've reproduced it here, but with the push A instruction to store the A bit until we're done with the ready. And then, of course, we load A with the read-write bit without the enable bit set, and we store that to port A, and that will turn off. That will make it so that the LCD controller is no longer pushing data onto the port B data bus. and then we load A with 111, which means we're going to set port B, the pins on port B back to output. Remember, we set them to input up here, so we're going to set them back to output. And then we're going to pull A off the stack, and we AND it with ADDR. And ADDR is, remember the RDY, the ready, that's that top order bit. ADDR, that's the low order bits. So by ANDing it with ADDR, we get rid of that status, that ready bit, because we don't want that. And now the accumulator, the A register, is storing the LCD address counter value. So that gets the LCD address. So here we jump that to get the LCD address, and we have that in the A register. And then we load Y with 80, and that's going to be that 81st data byte that we reserved. So it's 0 through 80, and this is decimal, not hex here. So 0 through 80, and then so now we're storing at LCD vec comma Y. So we're storing this address in that last position. Then I set the LCD address counter to 0. So I've saved the address counter. Now I'm setting it to 0, and I'm going to start reading through the data. So I'm loading Y with 79. That's going to be the 80th bit, because 0 through 79 gives you 80. And then I call LCD read to read the next byte. Let's go take a look at LCD read. So LCD read, it outputs on the A register a byte from the address counter. And as a side effect, when you do this read instruction on the LCD controller will increment the address counter or decrement it depending on the mode, but we set the mode to increment specifically, so it will increment it. So we call LCD wait to wait till it's ready. Then we set all the pins on port B to input, and we store that in the data direction register for port B. Then we set the read write bit to read, and we also set the register select, because now we're going to be reading from the data register, and so we need the register select bit to be set to 1, and we store that to port A, and then we OR those together along with the enable bit. We set the enable bit, and that will now cause the LCD controller to put the data that's at the address counter onto the port B data bus. And so we store that to port A, and now we load A from what's on port B, because now the data that's interested is there. And we push A onto the stack because we need to save it. And then we're going to load A with the read write and the RS bits, but not the enable bit. So that's going to turn off the enable bit and therefore tell the LCD controller to stop putting the data on the port B. And then we're going to store that to port A to actually cause that to happen. And then we load A with all ones to set the pins on port B to output and store that in the data direction register for port B. Then remember, we stored A, and we pushed A onto the stack up here after we loaded it for port B. So we pull it off and return to subroutine. So we read the next byte, and we incremented. We read the next byte, and that increments the address counter. And then we store that to LCD vec Y, and then we decrement Y. So you'll notice that we're counting up on the address counter on the LCD. So we're taking what was on there, and we're starting here, and we're going up. But we're decrementing on Y. We're actually going from the top down. So we're putting the first bit into the last memory location, and the first byte into the last memory location. The second byte will be into the second to last memory location, and so forth. But it doesn't matter the order that we store it, as long as we read it out in the same order. So we decrement Y, and then we branch if plus to get the LCD byte. Why branch if plus? Well, in the 6502, plus means 0 or a positive number. So if we get to the point where we have a negative number, because we've decremented down to FF, from 00 to FF, then that means that we're done after this decrement. But we do need to get the byte, when Y gets to 0, we do need to still get that byte, because that'll be the 80th of our 80 bytes that we're reading out of the memory. So that's why you do branch if plus to go back to LCD byte. So even if Y is 0, this will branch to get the next one, get the one that's to get the last byte and store that at the LCD vec plus 0 index position or memory location, which will be, of course, LCD vec, the location pointed to at LCD vec, which will be that LCD data location. And then decrement Y will make it go negative, and then we'll drop down to publish the results to the LCD. And this works just like I showed before. We publish the results to the LCD, and everything is the same until we get to the byte where we're doing the wait. If you remember, after we hit this wait instruction, we're now waiting, and now we're displaying the actual. Instead of displaying what's on the screen, we're displaying, or what was on the screen before, we're displaying the register information that we want for the debugger. Once we push the button from that, so if we push the button here, when this is displayed, then we need to go and put everything back the way it was on the LCD controller. So we need to set the LCD address counter to 0, and we need to go to the LCD instruction for that. So we set the address counter to 0, and then we load a 7-9. So this is that the top byte, which is the first byte in our from our data in the LCD controller. And then we just do the opposite of what we did before. So now we load from LCD vec comma Y, and we do a print car because we just print that out, and that will print it at the 0 position, and it will move the address pointer to the next position just like usual. We decrement Y, and again we keep going until we get past 0 all the way to negative or to FF, and then we load Y80. This is where we stored the address counter. So we load Y with that, and then we load A with LCD vec comma Y, which brings us to LCD data plus 80. And that is the location of the address that we stored the address counter from the LCD controller. So we OR that with 10000 to set the address command bit and to set the address counter. So this sets the address command. So this is the command to set the address. You give it a 1, and then you set the address after that. And of course, we want all zeros. We're ORing with an A, so we have all zeros here. So only wherever a bit is set, there'll be a bit set in the A register at that point. So this basically just has the effect of setting the address command bit and leaving the address itself alone. And then we call LCD instruction, and that will insert the address. That'll change the address counter to what we specify in these 7 bits. And then we call LCD init to reinitialize the LCD back to its primary mode, the mode that it was in when we started. And then we just, now we're back to restoring the A and X and Y registers and returning from the interrupt just like we did before. So this part here is the new part following this wait. And that's really all there is to it. Not a long video today. But that lets me step through and see everything and then put the LCD controller back where it was. Now, if you're using the LCD controller with weird modes, I am not taking that into account here yet, I don't believe. LCD init. Let's see. Yeah, you can see when I say publish the results to LCD, I'm just calling LCD init here. And so if the mode that we started with is not what we want with LCD init, then this is going to be a strange mode, and things might, like if you were setting it up to write in reverse, for example, then everything would end up in reverse. So really this LCD init should get its own initialization subroutine that initializes specifically to the counter increment mode. But I didn't do that. That could be an assignment for you in the future to see if you can write a routine here that would a separate LCD init that initializes the LCD in the mode that we want for this, but use a different mode in the main program. Now there is something interesting that I wanted to share with you. that at least I found it interesting, and also maybe somebody could help me with it. When I first wrote this, I did not put this weight up here to stop. I put the weight after the restoration of the LCD screen. So let me go put that in there. So I put the weight here instead. So instead what it would do is it would display the registers first, and then it would just show you what was there. Now the problem with that was that it would be showing you what was happening in the next instruction after whatever was displayed, so you wouldn't see what caused the display to look like it did. You'd be seeing what, before you saw what was on the display, you'd be seeing what it looked like next. Let me see if I can show that to you. So let me program this chip. I'm using this Tom EEPROM program that I built, which I like very much. And we're programming. All right, and put that back into the computer. So I start here, I press reset, and it brings up the W like it did before. That hasn't changed. I put it in debug mode, and I start single stepping. And here you can see now it's pointing a 6.9, and nothing's changed yet. 6.9, and nothing's changed yet. And now it's jumped to a 0.1 here, and PC is at C26B, and then it's just going to stay there and do that. And that's the problem I've been having. But here's what I found. This is very strange. If I'm running this at 10 megahertz like I normally do with this computer, but if I remove this down to 2.5 megahertz, here I'm using, you've seen this before in my videos if you've been watching, 74 HCT 4040 counter. So this is a 12-bit counter. That lets me divide this clock rate down a lot to quite a slow speed. But right here, I'm going to put it at 2.5 megahertz. Now let me rerun this. There we go. And then put it in debug mode and start stepping through it. And now it works. Now it's working normally. But you'll notice that it's displaying. It'll display the next thing before it showed it. So here's a 7.3, and that's going to be the S, but it's displaying an E here. You see, so it's already kind of past what you would see there. It's already moved past what it's showing you on the screen, and so that could be confusing, I think. So that was why I moved the break instruction or the wait instruction from down here to up here, was to fix that. But what was odd was then doing that. We gotta keep going. So that's why I moved it up here, was to get rid of that problem. So that changed it so that when I did that, changed it so that this worked kind of the way you'd expect, the way I showed you before, that it shows what the display is, and then it shows the instruction that caused that. And I like that better. But the other weird thing was that it made it possible to run this to run this at 10 megahertz instead of at 2.5. So here you can see that I'm running it at 2.5 and it's working. But if I were to move this to this pin, which would be at 5 megahertz, then it, oops, I hit reset there instead. But then it, let me start over. Oh, forgot to put it in the. So I'm running this at 5 megahertz, and it then behaves strangely after the eye. Like it gets through the eye okay, and then well, now it's working. Now before it wasn't working at 5 megahertz. Oh yeah, here you can see it's doing weird things. Like it put the N where the T is supposed to be. And now it says with witness, it says wine. And now it's, you can see program counter is C26B, and there's a 03 in the A register, and it's just staying there. It's just not working right. So, but if I go back and, recompile this with the putting it back the way it was, and reprogram that chip. So I changed it here and I've reprogrammed it. And now if I run this, put it in debug mode, and now I'm running at 10 megahertz, and it works just fine. Take it out of debug mode, finish the rest one more time, and then boop. So maybe somebody out there could explain to me why just moving this wait command would change the rate at which the clock speed at which I can run this. So if you made it all the way to the end here with me, thank you very much. I hope you like what I'm doing here. If you do, please click like on the video and maybe even subscribe. It really encourages me a lot to continue, and I see people are enjoying what I do. Thank you very much. I will talk to you again soon.